Calculations with Ka. Calculating Ka from the pH. The first type of calculation is the calculation of the value of Ka for an acid from the measured value of the pH for a given concentration of the acid. Here is a problem. The pH of a 0.10 molar solution of formic acid, HCOOH, at 25 degrees Celsius is 2.38. Calculate Ka for formic acid at this temperature. The dissociation equilibrium is HCOOH plus H2O in equilibrium with H3O plus HCOO minus. The equilibrium expression is Ka equals the concentration of H3O plus times the concentration of HCOO minus over the concentration of HCOOH. To calculate the value of Ka, we will need the equilibrium concentrations of H3O plus, HCOO minus, and HCOOH. We are only given the initial concentration of the HCOOH and the pH of the solution, which is at equilibrium. We can get the concentration of H3O plus from the pH, and the concentration of HCOO minus must be the same since we started with the undissociated acid. The pH equals the minus log of the concentration of H3O plus. So 2.38 equals minus the log of the concentration of H3O plus, and minus 2.38 equals the log of H3O plus. Raising both sides to that power of 10, we get 10 to the minus 2.38 equals 10 to the log of the concentration of H3O plus, and we know that 10 raised to the log of anything is that thing, so that equals the concentration of H3O plus. Doing out the math, we get that 4.2 times 10 to the minus third equals the concentration of H3O plus, which equals the concentration of HCOO minus. Now we set up the icebox, which is shown here with the initial conditions for the problem. The equilibrium concentration of H3O plus and the equilibrium concentration of HCOO minus we just calculated to be 4.2 times 10 to the minus third, which we place in the equilibrium row. This means, since we started with 0 of each of these, that the change for each was plus 4.2 times 10 to the minus third. Therefore, the change for the concentration of HCOOH is minus 4.2 times 10 to the minus third. This allows us to calculate the equilibrium value for the concentration of HCOOH, which is 0.10 minus 0.0042, which equals 0.0958, which must be rounded to the second decimal place, or 0.10. Now we take the values from the equilibrium row and plug them into the equilibrium expression, which gives us Ka equals 4.2 times 10 to the minus third squared over 0.10. Doing out the math gives us Ka equals 1.8 times 10 to the minus fourth. The percent ionization or percent dissociation is an interesting number to calculate. It tells us what percentage of the molecules are broken apart. To calculate the percent dissociation or ionization, we take the equilibrium concentration of H3O plus and divide it by the initial concentration of the acid, then multiply by 100 to convert to percent. In this example, the equilibrium concentration of H3O plus is 4.2 times 10 to the minus 3, and the initial concentration of HCOOH is 0.10. Plugging these numbers into the formula, we get that the percent ionization is 4.2%. Next, let's do an example of calculating the pH for a weak acid when we know the value of Ka and the initial concentration of the acid. Here's a problem. Calculate the pH of a 0.30 molar solution of acetic acid, HC2H3O2, at 25 degrees Celsius. Ka for acetic acid at 25 degrees Celsius is 1.8 times 10 to the minus fifth. The acid dissociation reaction is HC2H3O2 plus H2O in equilibrium with H3O plus C2H3O2 minus. And the equilibrium expression is Ka equals concentration of H3O plus times the concentration of C2H3O2 minus divided by the concentration of HC2H3O2. Let's go to the icebox. Here's the table with our initial concentrations, 0.30 for acetic acid and 0 for both H3O plus and the acetate ion. Since we have no products, the products must be positive in the change row and the reactants must be negative. So we get minus X, and plus X. The equilibrium row would then be 0.30 minus X, and X. If X is very small compared to 0.30, then it can be ignored in the expression 0.30 minus X. Substituting the values in the equilibrium row into the equilibrium expression, we get 1.8 times 10 to the minus fifth, the value of K, equals X squared over 0.30 minus X. If X is small enough to ignore, then this will simplify to 1.8 times 10 to the minus fifth equals X squared over 0.30. Should we use the simplification? The answer is yes, at least as a first approximation, because it makes the equation so much easier to solve. We can check to see whether it's a good assumption using the percent ionization. If the percent ionization is less than 10%, then the assumption is acceptable. If less than 5%, then the assumption is a good one. If less than 1%, the assumption is excellent. If the percent dissociation is greater than 10%, then the quadratic equation must be used to solve the problem. The equation becomes 1.8 times 10 to the minus fifth times 0.30 equals X squared, or 5.4 times 10 to the minus sixth equals X squared, and X equals 2.3 times 10 to the minus third. So, the concentration of H3O plus equals 2.3 times 10 to the minus third molar. The pH equals minus the log of the concentration of H plus, which equals minus the log of 2.3 times 10 to the minus 3, which gives us a pH of 2.64. Now let's check to see whether the assumption was good. Find the percent ionization. The percent ionization equals 2.3 times 10 to the minus 3 divided by 0.30 times 100. Calculating this, we get 0.77% ionized. So the assumption is an excellent one.